Hello, everyone. Welcome to Physics 205. So in this lecture, what I want to do is I want to do some examples where we actually add vectors together graphically. So using protractor and ruler. So in this first question here, we have this box and we have two forces exerted on the box. We have F1 pulling at an angle of 120 degrees. So measure from the positive x-axis 120 degrees. And it has a magnitude of 10 newtons. Then we have a second vector, F2, pulling at 0 degrees, so right along the x-axis, and it has a magnitude of 50 newtons. And what I want to do is I want to add those two vectors together to find the net force. So the net force, which sometimes we call the resultant force, is R vector or F net. I'll just call F net for this particular example, is simply going to be the sum of F1 and F2. I want to add those two vectors together, and I want to solve this problem graphically. Okay, so how do I do this? Well, the first thing I need to do is I need to have some type of conversion factor, because when I draw these vectors on the graph paper, then I have to know how long to draw them, right? These are in real world units of newtons in this case, but I need to convert that to centimeters to draw a particular centimeter so that they're proportional on the graph paper. So I'm going to choose some conversion factor. Let's say, I don't know, let's say 2 newtons is 1 centimeter. So we're going to choose a scale factor or conversion factor. This is also called a conversion factor of, let's say, 2 newtons is equal to 1 centimeter. That should give us reasonable lengths here. Okay, so how do I convert these? Well, I know that F1, which is 10 newtons, I want to convert that to centimeters. So remember, I can write the 2 newtons equals 1 centimeter. I can either write it as 2 newtons over 1 centimeter, or I can write it as 1 centimeter over 2 newtons, right? That's my unit conversion factor. But in this case, I want newtons to cancel and centimeters to survive. So I want to use the second one, right? I want 1 centimeter over 2 newtons. And if you work that out, you're going to find that that's going to give us 5 centimeters. So F1 should be drawn 5 centimeters in length. And then F2 is 15 newtons. Again, I'll multiply by 1 centimeter over 2 newtons. And that's going to turn out to be 7.5 centimeters. So if I draw at 7.5 centimeters, that will give me the correct length. Okay, so I'm going to do this on graph paper, but before I do that, let me just quickly show you like approximately what the answer should look like. So if I start with F1, I'll just add these tip to tail, but I won't do it exactly. I'll do it exactly in a minute on the graph paper. Then at 120 degrees, right, I have F1, so it's going to look something like this. So this is F1. This is 120 degrees. And then I want to start at the tip of F1, right? So sometimes what we do is we draw like a new coordinate system here. And then I want to draw F2. Well, F2 is at 0 degrees. So that's just going to the right. And remember, the way that you do this is you put the tail of F2. So I did the tail of F2 at the tip of F1. And then finally, to get my resultant vector, my net force, I draw a vector from the tail of the first vector, so that's from the origin, to the tip of the last one, in this case, the tip of the second one. So this would be F net. Now, how do I figure out the magnitude and direction? Well, what we're going to do is we can measure this length, right, in centimeters and convert back to newtons, so I know its magnitude. And then I can measure this angle here with the protractor to get the angle in degrees. Then I have the magnitude and direction of F net. Okay, so let me do that now on graph paper and show you how this works out. Okay, so I have some graph paper. I just drew like a typical XY coordinate system there so I can start. Now remember, F1 is at 120 degrees. So I take my protractor, make sure you line this up, right? So that 0 is off to the right, 90, and then 180 is to the left. And then we want 120 degrees. So I'm just going to make a little mark there. So 120 is about right here. And then I'll take my ruler and I want to draw a vector. What do we say F1 was? It was 5 centimeters, right? So I'll just start at 10 here and I'll go up to 5. So something like this. And you should always draw the arrow, right, on that vector. And you should label this. So this is F1. And then this angle here was 120 degrees. Okay, then I draw a new coordinate system. I'll just like dash it in here at the tip of F1. Something like that. And I want my new vector F2 to be at 0 degrees, right? So that's just going to be to the right in this case, directly to the right. So something like this. And I want that one to be, what was it, 7.5 centimeters. Actually, that's pretty close where that dot is. So something like that. So this is F2. And then was at 0 degrees. And finally, to get F net now, I draw a vector from the origin to, right, the tail of the first vector, which is really starting at the origin, to the tip of the second vector. So something like this. Again, I'll draw arrows there. This is my F net. Now, to get the magnitude, I simply measure this. So if I measure this, it turns out it's around, I mean, I'm using a thick marker here so that you guys can see this better, but normally you do this like with a pencil. So it'd be more exact. Let's say it's like 6.5 centimeters. So my F net is 6.5 centimeters. But I can convert that back to newtons because remember 2 centimeters was 2 newtons was 1 centimeter. So now I can multiply by 2 newtons over 1 centimeter. And that will be 13 newtons. And then if I measure this angle here, so with the protractor, I measure this angle. It turns out it's pretty close. It looks pretty close to 40 degrees here. So I'm going to say that this angle is 40 degrees. So that's our answer. So F net, that vector, has a magnitude of 13 newtons at around 40 degrees. Okay. And because it's graphical method, this is approximate, right? A better way to do this, and we'll explain this in the next video, is add these vectors analytically, add them mathematically using sines and cosines. That will be an exact method. In this case, it's good, but it's still an approximation because we make some errors with our drawing and our measurements. Okay, another example. Okay, in this example, you're told a train is moving west at 10 meters per second, and a passenger on a train runs north at 4 meters per second. What is the passenger's velocity relative to the ground? Okay, so this is a relative velocity problem. So you have to think about this first, but let me set this up for you. Really, the important part in this for this example is just adding the vectors ultimately together. If you don't totally understand this relative velocity, we'll learn more about this later. So the first point here is we need to know the velocity of the train relative to the ground. Well, that's given, right? Because it says a train is moving west at 10 meters a second. So that vector, which is a velocity now, and I have TG meaning train relative to ground, that's going to be 10 meters per second at 180 degrees, right? Because it's going to the west, it's pointing to the left. Then I also need to know the velocity of the passenger, the person relative to the train. So I have a velocity of PT, person relative to train, and that's going to be 4 meters per second. They're moving north, so we're going to call that 90 degrees. And then ultimately what I want to find is the passenger's velocity relative to the ground. Well, the velocity of the passenger relative to the ground here, so P relative to G, that's going to be the sum of the velocity of the passenger relative to the train plus the velocity of the train relative to the ground. If I add those two together, that gives me what I want, which is the velocity of the passenger relative to the ground. Okay, so if here, let me sketch this out to show you what this looks like. So the velocity of the train relative to the ground first, right? That's going to be, I'll just draw a coordinate system here. So velocity of train relative to ground, that's going to be to the left. So TG. Then I want the velocity of the passenger relative to the train. That's going north, right, 90 degrees. Right, this right here, by the way, was 180 degrees, like this, 180 degrees, right? That's west. And then if I go north, or 90 degrees, and since I'm adding these, or I'm adding tip to tail, that's going to be this vector like this. So this is velocity of passenger relative to train, right, where this is 90 degrees here. And then finally, if I want my answer, which is the velocity of the passenger relative to the ground, I just connect these, right? I draw a vector from the tail of the first, so from the tail of velocity of train relative to ground, that first vector, to the tip of the second one. So that would be like this. And that's the one I really want, right? That's the velocity of the passenger relative to the ground. And then again, I'll show you how to do this graphically on graph paper in a second, but I'm going to want to measure the length of that, convert back to velocities, right? Because I'm going to have some conversion factor. We'll figure that out in a second, what the conversion factor is. And then if I measure the angle here, that'll give me the direction of that velocity vector. Okay, so let's assume for a conversion, let's let 1 meter per second equal 1 centimeter. That seems reasonable, okay? So the first one, which is the velocity of the train relative to the ground, that was 10 meters per second. And I need to multiply it, so I have a unit conversion factor here right now. I have either 1 meter per second over 1 centimeter, or 1 centimeter over 1 meter per second. I want to use that second one, right? If I multiply by 1 centimeter over 1 meter per second, then this is going to give me like 10 centimeters. And then if I want velocity, I want person relative to train. Well, that was given as 4, right? The magnitude is 4 meters per second. So again, if I multiply by 1 centimeter over 1 meter per second, that's going to give me 4 centimeters. Okay, and so let me go to now the graph paper and we'll actually solve this problem. Okay, so again, I have my coordinate system drawn out. Now I drew it a little bit to the right because I know my answer is going to end up in the second quadrant. So I want to make sure I have enough room to draw these vectors. I need to draw the first vector, which is the velocity of the train relative to the ground. And that was at 180 degrees, right? So remember, if you do 180 degrees, that's going to be exactly along the negative x-axis, right? So this is 0 all the way to 180. So, and I want to draw that, what was the length? 10 centimeters. So I'll put this at 10. So that's going to be something like this, right? It's going to be right along that negative x-axis, and it's going to end up right here. So that was the velocity of the train relative to the ground. Okay, and then at the tip of that vector, again, if you want, you can like dash in a new coordinate system here. I want to draw a vector, right? The velocity of the person relative to the train, and it's at 90 degrees. So it's going straight up. So I'll put my protractor there. At 90 degrees, I'll draw a little mark. And then I'm going to draw this length. What was the length? 4 centimeters, right? So again, I'm just going to go, actually, I'll do it this way. So I want to go up to 4 centimeters. So something like that. So this is the velocity of the person relative to the train. Okay, so now to add these together, I simply draw a vector from the origin, right, the tail of the first to the tip of the last one. So that's going to be like this. Draw an arrow there. So this is the velocity of the person relative to the ground, right? That's what we wanted. If we add the velocity of the person relative to the train plus velocity of the train relative to the ground, we get the velocity of person relative to the ground. Now, how do I find the magnitude? I simply measure this, right? So if you measure this, I want to be in centimeters. It turns out it's going to be around, let's see, maybe 10.8 centimeters. So I'll say velocity of person relative to the ground, that magnitude is 10.8 centimeters. Now, if I multiply by my conversion factor, remember, I can use now 1 meter per second equals 1 centimeter. So that's easy, right? Multiply by 1. You're going to get 10.8 meters per second. So that's my magnitude. And then to find my direction, I use my protractor. So my protractor here. And I just read off that value. If you read out, in this case, I have to use the inside scale, right? It looks like 158 degrees. Right, be careful. Don't use the outside scale. I mean, you can and subtract from 180, but if you use the inside scale here, it goes from 0 to 180. It depends on how your protractor is designed. So this angle is going to be around 158 degrees. Okay. The other way you could do this is you could measure this angle. You could measure the reference angle, which is like 22 degrees. So you can measure this angle, 22 degrees, but then you'd have to say like north of west, right? You'd have to give it more information. So if I just do it the way I did it, I could say velocity of person relative to ground is equal to 10.8 meters per second at 158 degrees. If I use that reference angle, which I could do, then this would be 10.8 meters per second at 22 degrees north of west. You'd have to define to make sure that the person knows that the vector is in the second quadrant, right? As long as you give enough information so that we know that the vector is in the second quadrant. Okay, great. Let's do a little bit with vector subtraction now. Okay, so with subtraction of vectors, subtraction is really the same as adding the opposite, right? Just as with real numbers, right? If I do, say, 2 minus 5, that's the same thing as adding 2 plus the opposite of 5, which is -5, right? In both cases, I'm going to get -3 for my answer. Same thing with vectors. If I have this vector A here, drawn like this, and I have vector B, and I want to subtract, I want to get a resultant vector, I'm calling it R now, which is A minus B. That's the same thing as doing A plus -B. And why do we do this? Because we know how to add vectors, right? We just add tip to tail. So subtraction, we turn into an addition problem. Now the question is, what is -B? -B is really the same thing as -1 times B. And all that does is it reverses the direction of the vector. Okay, it changes both of the components. The x component and y component change their sign. So what that does ultimately is it reverses the direction. So if this were originally b, then minus b will be the same length, but in exact opposite direction. Okay, so if this is at 0 degrees, then minus b is going to be at 180 degrees. Okay, so now if I want to add, if I want to subtract these, I'm basically turned it into an addition problem now, right? So let me just sketch this out here. So I would start with vector A. So they'd be drawn like this. Then again, I go to a new coordinate system here. So I'll just dash it in there. And now I'm adding -B, but so -B, the tail of -B is going to be at the tip of A. So it'll be at 180 degrees like this. So I'm just adding negative b instead of b. And then that will give me the resultant here. So remember, I draw from the tail of the first, so the tail of A, which is at the origin, to the tip of the second one. And then that actually is now going to be my resultant. That is equal to A minus B. Okay, so that would be the vector. And then, of course, if we're doing this graphically, we'd have to measure the length. We'd have to have some conversion factor and measure the length of that to convert it back to whatever the units are, and then measure the angle of the protractor. Okay, so here's an example. Let's say I'm given that v initial, so this is like a velocity, right? The initial velocity is 10 meters per second at 90 degrees, and the final velocity is 5 meters per second at 90 degrees. And I want to find the change in velocity, which change is always defined as final minus initial. So this is really a vector subtraction problem, right? But immediately I'm going to turn it into a vector addition. Really, what I really want is delta v is going to be v final, that'll be the same. But instead of subtracting, I'm going to add the opposite of v initial, which is negative v initial. So it's just going to change the direction of whatever v initial is. So if we actually sketch this out, so basically v initial, right, is 10 meters per second at 90 degrees. So that's going to be like straight up like this. And then v final is also at 90 degrees, so it's straight up, and it's going to be 5, right? So it's like half the length here, v final. So if I want to do v final minus v initial, first of all, if v initial is pointing straight up, right, 90 degrees, and it has that length, what is negative v initial going to look like? Well, it's going to look like this, right? It's going to be same length, but it'll be pointing down, right? Same length, but pointing down. So this is like negative v initial. It's pointing down. So if I want to add those two together, I'm going to draw this again. I would start by drawing v final, because that one is okay. So that one would just be straight up. Again, you'd have some conversion factor, so you know how long to draw this. I'm just sketching it right now. So that's v final. And then I want to add negative v initial to it, right? Because I want v final minus v initial, which is the same as v final plus a negative v initial. So now I go to that negative v initial, and I put its tail at the tip of v final, so something like this. And then I'm going to draw all the way down, right? It's drawn down. So this is like negative v initial. And then finally, what is my result? What is my v final minus v initial? Well, it's going to be the vector that starts at the tail of the first, so the tail of v final, to the tip of the last one, which is the tip of v initial. It's also going to be pointing straight down like this. It'll be just this length right here, though. So this red vector is my delta v, right? That's v final minus v initial. Okay, so, and basically, if you work this out, right, we can actually do this just by thinking about this, right? We can do it mathematically because everything is in the same direction. If v final is 5 meters per second, right, so this is 5 meters per second, this length, and I add negative v initial, which is like now negative 10, then what is delta v going to be? Well, its length here, its magnitude is going to be 5, right? 5 meters per second. And what's the direction? The direction, so the delta v is going to be 5 meters per second at, and since it's pointing straight down, this angle here, if I measure this angle, is 270 degrees, right? Straight down. So at 270 degrees. So that would be my answer, right? It's pointing south. So 5 meters per second at 270 degrees. And we could do this graphically as well, right? If I have a conversion factor, then if I measure this delta v and convert back 2 meters per second, I should get around 5 meters per second. And then the direction we already know is straight down south, so it's 270 degrees. Okay, let's do one more example where we actually do it out graphically. So here's the last example I want to do. So you're told that the R you can think of as like a position vector. So the initial position is given as 1,000 meters at 225 degrees. And then the final position is given as 500 meters at 290 degrees. And we want to find the change in position, which is really the displacement. So this delta R here is really displacement, although it's two-dimensional displacement. So it's going to be R final minus R initial. Or if we write this out as an addition, because ultimately we want to add vectors, right? We know how to add vectors. So this will be R final plus minus R initial, the opposite of R initial. Okay, so first thing, let's use some type of conversion factor. So let's say, I don't know, 200 meters is equal to 1 centimeter. Right, that's our unit conversion factor. So our initial for the magnitude, it was 1,000 meters. I want to multiply by, so in this case, if I use this, right, 1 centimeter over 200 meters, that will work. So I'll multiply by 1 centimeter over 200 meters, and that will give me 5 centimeters. And then for our final, this is 500 meters. So I'll multiply by 1 centimeter over 200 meters. And that will give me like maybe 2.5. This might be a little small, this picture. And again, you guys are free to choose whatever you want as this unit conversion factor. Like if you want to say 100 meters is 1 centimeter, then it'll be like twice as long. And that might be better. You just want to make sure you don't want it too long so that it goes off your graph paper. So you kind of have to, it's your choice, but you want to make sure it's like reasonable length on the graph paper. Okay, so what is this going to look like here? Let me sketch it out first. And then we'll actually do it on the graph paper. So it looks like, let's see, our final is going to be 290 degrees, right? So that's like, if I start at the positive X, go all around here, this is 270, and then like another 20, that will be 290. So it looks like that first vector is going to be something like this. And then our initial is at 225. So this is like 180 plus another, what, 45? So I guess it's going to be right in that third quadrant. So that'll look something like this. Right? And it's twice as long, right? Because it's 1,000 meters or 5 centimeters as opposed to 2.5. So this is our initial. This is our initial. Okay, but when I do this problem out, I want to do R final plus negative R initial. So what direction is negative R initial? Well, it has the same length as R initial, right? So this length is to be the same, but in the opposite direction. So R initial with a negative in front of it, negative R initial is going to look something like this. So if I want to add R final to negative R initial, I need to move the tail of R initial to the tip of R final. So let's say like this. Remember, this was negative R initial. So now I'm adding R final plus negative R initial. And then if I draw my resultant vector, I'm starting from the tail of the tail of R final to the tip of negative R initial. And that's going to be my delta R. Looks like our answer is going to be somewhere in that first quadrant, okay? And we'll have to do it out to find out exactly where it ends up being. All right, so let's work this out. Okay, so the first thing I want to draw is R final. And remember, R final was at 290 degrees. So how do we figure that out? Well, protractor, as you can see, only goes to 180, right? So we want to go 180 And we want to go an additional, how many degrees? I guess we needed to go an additional, I guess 110, right? So 290 minus 180 would be 110. So if I flip the protractor over, and I start from here and go 110, that's going to be somewhere down here. So let's say right there. And I want that vector to be of length. What was it? Our final was 2.5 centimeters, right? So pretty short here, 2.5 centimeters. So it might have been better if I made it slightly longer in my conversion, but I didn't, so it's okay. I'm just going to draw this 2.5 centimeters, so something like that. Right, so this is our final. Okay, and then, so if you want, you can draw like a little coordinate system here at the end, dash it in. And now from that tip, I want to draw my negative R initial. Remember, R initial was down like this. Like, remember, it was in the third quadrant at 225 degrees. So if we reverse that, remember, negative R initial is going to go the opposite way. So it's basically going to be at 45 degrees. So using my protractor, I'm at the tip of R final. I now want to draw a vector at 45 degrees because I want to draw my negative R initial at 45 degrees. So that'll be something like this. And what was the length? I guess it was 5 centimeters, right? So here, I'll just start this at like 10. Again, it's hard to see this because I'm using a bright marker, but you'll have better luck probably with like a pencil. Okay, so I'm gonna go 5 centimeters. I'm at 45 degrees, so it's gonna look something like this. So remember, this was negative R initial. Okay, and then finally, to figure out my resultant, R final minus R initial, that's going to be drawn from the tail of the first, the tail of R final, to the tip of negative R initial. So that'll look something like this. Remember to put your arrowheads there. So this is my delta R, right? That's what I was trying to find. This is actually R final minus R initial. Okay, how do I figure out the magnitude? Well, I can just measure the length of this, right? So if you measure the length of this, it turns out, again, it's hard to see here, maybe 4.6 centimeters. So I'm going to say delta R is 4.6 centimeters. But then I'm going to convert back to meters, right? So I have to multiply by, remember our conversion factor was like 200 meters is 1 centimeter. So if you do that, you're going to find that this is 920 meters, right? We're back to real world units. So the real world units is 920 meters. And then to get the angle, I just simply measure it with a protractor. Again, it's kind of difficult here because I'm using such thick lines with the marker, but it turns out it's around, if you extend this, it's around, should be around 16, maybe getting 15, but I'll put 16. So this angle here is 16 degrees. So that means my delta R, that vector is going to be 920 meters. This is real world units now at 16 degrees. And we don't have to say like north of east because 16 degrees is always defined from the positive x counterclockwise, right? If you want to, you could say north of east if you want to be even more clear. But if I just give an angle, it's always assumed it's measured in the positive x counterclockwise. Okay, so that should give you a good idea as to how to do how to add vectors using graphical method or how to subtract vectors using graphical method. And remember, subtraction is just like addition, except you're adding the opposite of that second vector. Okay, we'll get plenty more practice in lecture and in lab. We have a whole lab where we add force vectors together and compare it to an experimental result where we use something called a Kennan force platform. So we'll get a lot of experience with graphical addition of vectors. All right, great, thanks.